Alright, so now that we have run this simulation for a little while, it looks like it has converged. Now, one thing that I forgot to mention is the stopping criterion node over here. When, as you can see down here at the bottom in the output window, it says stopping criteria maximum steps satisfied. There's a node over here underneath the regions, derived parts, and the solvers nodes. It says stopping criteria. You click on the maximum steps, it has the number of steps that the simulation will run for until it stops automatically, whether or not it has converged. Now, usually you need to manually monitor if it's converged and just keep increasing the maximum steps if you don't think it has. In this case, it ran for 1,000 steps, and it looks like it's converged just fine. So we will not increase it, but if necessary, you could increase the number of steps and run it for longer. So let's take a look at our, oh, actually we haven't made a vector scene yet. So let's make a vector scene to represent velocity profiles. Because we use the Bose-esque model, let's change this to velocity. Because we use the Bose-esque model, we will have some natural circulation happening. And that natural circulation can be seen in the velocity profiles of the fluid. So they've already pre-selected velocity as our vector field. We're going to come here to the parts, and we're going to choose our water part and open. Oh, actually, sorry, we're not going to choose our water part. We're going to choose our derived parts right here. Create this, and look at that. We got some vectors there. Now this is kind of hard to see, but it's a bunch of little individual arrows pointing in directions, representing the motion of the fluid. This is a difficult way to see what's actually happening. If you click on vector, the node here, and go to display mode and change it to line integral convolution, that looks a lot prettier. Now be warned, it does take a lot of memory to generate this, so if you're on a slow computer, this may really slow up your computer. It might just be freezing up, so be aware. But look at how pretty that is. It's showing, as expected, along the heated edge, the fluid is going up this direction and then kind of swirling out into these eddies, these small eddies. So that's exactly what we'd expect. This is great. So this is one way to visualize your solution. Obviously, the other way is with this temperature scene and this temperature monitor plot. However, to present your results, a better way is to use something called a line probe, because you can slap this on a slide or something, but it's not the most technical presentation. So if we want to see, for example, what the temperature is at a certain elevation as we go straight across this cylinder, we can create a line probe, and that's under derived parts again. So we're going to come here, new part, probe, line, and it'll give us a view of where that line is. So basically this is going to be taking data from this spot to this spot using this number of points. So we're going to increase that actually to be about 100. And then we will, I'm fine with these, whatever points this shows. It looks like about 0, -1, 0.05, but in the future you could change that if you wanted. Actually, and I'm going to change the z value to be about 0.09 on both of these, because I want to capture those different temperature profiles at the top. Okay, make sure you switch this to no displayer, just like we did with the planes the other day. We are going to click create and close. Okay, and then we're going to open this line probe and create a we're going to create a plot using the line probe, but we'll probably do that in the next video. So that's how you create a line probe.